Assalamualaikum and hi, my name is Siti Hajar Binti Hasni and my student number is 2024424374. I have been supervised by S.R. Zaki bin Ahmad Dahlan and also co-supervised by Dr. Khairul Effendi bin Hashim. Today, I want to present about my research, which is 3D landscape modeling using UAV photogrammetry and Revit. Introduction: Integration of BIM, Autodesk Revit and UAV mapping technology for landscape, project planning and management improve planning, visualization and project management efficiency. Enhance stakeholder collaboration during the design and planning process to support evaluation of design impacts on community and the environment. This also can help reduce flash flood risk through informed and effective design solutions. There are two problem statements in this research. Firstly, failures in landscape planning or land development. Poor urban planning and environmental issues increase the frequency of flash flood and waterlogging. Secondly, uncontrolled topographical changes without appropriate 3D analysis. The fast expansion of urban areas is converting natural surface into hard materials and stopping rainwater from soaking into the soil. Uncontrolled topographical changes that are not properly 3D analysis can lead to flash flood and land development problems. The aim for this research is to study the use of Revit and UAV photogrammetry in 3D landscape modeling for better environmental risk assessment and flash flood mitigation. There are three objectives for this research: to generate accurate topographic models of institutional areas using UAV photogrammetry data. Second, to design a detailed 3D landscape model in Revit using UAV photogrammetry data. And thirdly is to analyze environmental risk and flash flood prone areas using a 3D landscape model. Methodology: there are four phases for methodology. First one is planning. In planning, we need to identify the site selection first. My site selection is at academic height UiTM Arabalis. Next, we need to recognize the site which are identified to place the 5 GCPs and 10 BPs before collect the data. The last step in phase 1 is flood planning. The flood altitude is set as 18 meters and the image overlap is for front lap is 18% and side lap is 17%. The coverage area for this study area is 1.55 hectares and the flood time is 1 minute 40 seconds. And the camera setting as auto. Next, phase 2 is data collection. For my research, I have been collect two types of data, which are photogrammetry data and do the GPS observation. For photogrammetry data, I have been collect the 19 area image that have been captured by the DJI Phantom 4. While for the GPS observation, I have collect 5 GCPs and 10 BPs point using RTK observation is data processing. In this phase, I have processed the area image in Agisoft Metasheet. The first step to process the area image is align the image. Then we can proceed to process the dense point cloud. The point cloud that have been processed are around 52 million. The dense point cloud, we can process the 3D mesh models, DSM or DEM, and shows the highest elevation, which is 27.1 PM data. We can get the contour and the accuracy assessment analysis. To get the result of the slope and flow direction, I will process it using Artist Pro. The slope map shows the color shades starting from dark green, which is 0 degree to 2nd degree, to red, which is 44 degree to 84 degree. The dominant slopes in the map are those which are between 0 degree to 10 degree, shown in dark and light green. This range considered as flat areas and hence good for building development, construction of road and walkways because of their stability and low risk of soil erosion. The steepest slopes, which are above 24 degree, are mostly in areas of road embankments, cut and freeze drainage areas and elevated topographical landforms and are shown in orange and red colors. Next, flow direction. Use the D8 flow direction algorithm in the formation of this map means that each color depicts one of the 8 flow direction available, which is 1, 2, 4, 8, 16, 32, 64 and 128, showing how the water moved from each cell to the steepest downslope. From the slope and flow direction result, I can get the flash flood risk result. Flash flood risk is classified into 6 levels, ranging from level 1, which is very high risk, to level 6, which is very low risk. The study area is mainly dominated by level 2 and level 3 zones, indicating low to moderate flood susceptibility. The high risk zones, which is level 1, are concentrated near depressions and drainage accumulation areas. For low risk zones, which is level 4 to 6, are generally found in drainage corridors and elevated areas with efficient runoff movement. The academic height has predominantly low to moderate flood risk, but targeted mitigation is required in identified high-risk areas to support sustainable landscape planning and effective stormwater management. Next, I will propose the structure for the landscape plan at Autodesk Revit. As we can see, the proposed structure in the landscape plan have retention pond, recreational area, circular landscape garden, pedestrian walkways, open green space, tree and ornamental plantings, main road, and lastly, the natural drainage and runoff management features. And the final output we get, which is is the 3D landscape analysis. The first result is an accurate 3D topographic models of institutional areas using UAV photogrammetry data. These accurate topographic models help to design the landscape plan. Next, the second result is a detailed 2D landscape model. The elevations shows ranging from 4 meter to 19 meter. The lowest elevation, which is 4 meter, is located in the southwestern area, while the highest elevation, 19 meter, is in the northeastern area. The elevation gradually increases from the southwest toward of the central and northern parts of the site. The landscape features are strategically placed according to the site's elevation and terrain characteristic. The open green space, which is between 11 to 40 meter, is promote effective drainage while maintaining the visual appeal. And the higher elevation, which is 18 meter to 19 meter, function as natural drainage divides, directing surface runoff away from recreational areas. For the last result, we can analyze the environmental risk and flash flood points areas using a 3D landscape model. There are 3 flood risk levels, which is high, moderate, and low. For the high risk areas, low elevation areas prone to runoff accumulation and flooding. For the mitigation measures is drainage channels and retention ponds. And for the moderate risk areas, which is moderate slope with potential runoff during prolonged rainfall, the recommended measures is vegetated swales and additional landscaping. And lastly, for the low risk areas is a flat terrain with efficient natural drainage. The key finding is flood risk is influenced by topography and runoff patterns, which is appropriate mitigation, improve stormwater management, and flood control. In conclusion, UAV photogrammetry, GIS, and BIM integration provides an effective method for 3D landscape modeling and flash flood risk assessment. High-resolution UAV data enable accurate terrain and floodfront area analysis. Flood risk mapping help identify suitable mitigation measures such as retention ponds, drainage channels, and vegetated swales. The UAV BIM workflow improves planning accuracy, supports informed decision-making, and promotes sustainable landscape development. There are 3 recommendations for this research. Firstly, utilize UAV LiDAR technology to improve terrain representation in densely vegetated areas and enhance elevation accuracy. Secondly, develop a complete 3D Revit model incorporating flood mitigation features to evaluate their effectiveness before implementation. And lastly, investigate the effectiveness of BIM as a decision support tool for environmental risk management and sustainable campus planning.